Okay, as a quick review, earlier we looked at this selection sort algorithm. I've updated it just a little bit, so it generically takes in two lists of integers. One will be the input list, and the other will be the sorted output list. And it will continue to remove items from the input list as long as there are items in the input list. And what it'll do is it'll look through the entire input list using a loop, and it'll try and find the minimum item. So there's a for loop that goes through searching for the minimum item. Once that minimum item's been found, it will append it on to the end of the output, the sorted list, and go ahead and remove it from the input list. Okay, while we're here, let's note that we're using a couple of different methods of the list interface. So we've got these two lists, input and sorted, and it looks like on input we're checking the size. We're also using the get method, and on sorted we're using the add method, and on input we're also using the remove method. So it looks like we've got a total of 4 different list methods that are being used: size, get, add, and remove. So as we're doing our analysis to try and identify the time complexity of this, we'll need to look at those 4 different methods. So this is the source code for the java.util.ArrayList class. If you really want to improve your coding proficiency, look at existing code, particularly code done by professional programmers that have a lot of experience, because you can learn an awful lot from the various tricks that they do and their general style. So I'm going to skim through this. I'm just going to focus on some of the details. So it's going to store an array of type E. We'll look at that in just a bit. Okay, so it's got a size variable that's an integer, and it's got element data, which is an array of objects. So this is the element data is where it's actually going to store the individual items. So we'd identified that our method for sorting uses 4 different methods. So it uses size, get, remove, and add. So let's go ahead and look at a few of those. So I'm going to go ahead and focus on the size method first. So I'm just searching through this file for size, and here it is. And we can see that all it's doing is it's returning the member variable size. So I'm just going to go ahead and make a quick note that basically it's just returning a simple integer. So this would be a constant time operation, so an O of 1 sort of operation. Okay, now that we understand size, let's go ahead and look at add. So I'm going to search for add. First, it drops us to this method that takes 3 different parameters. It says it's a helper method. It's private. That's not the one we're calling in the sort. So let's go ahead and search for the one we're calling in the sort. Here it is. This is a public add that appends to the end. So a couple of things here. Notice that it adds 1 to a mod count. That'd be a constant time operation. And then it calls that other add, the one that we just went by. So this is something that we're going to have to look at in more detail. And then it returns true, another constant time operation. So in order to determine how much time or how many operations this add does, we're going to have to look at the more complicated add with 3 parameters. Okay, so I'm just going to make a note of that everything kind of hinges on this version of add. Okay, so let's go ahead and look at that version of add. So we'll go back up and take a look at it. Okay, so notice that it has an if statement. So if this if statement executes, we'll have to think seriously about how much work it does. But let's think about what if it doesn't execute. If it doesn't execute, we're going to fall through and do these 2 lines of code. If it does execute, we'll fall through and do these 2 lines of code. The first one's assigning a value to an array. If you remember, arrays have this random access property where it doesn't really matter what index we're putting something into. We think of it as taking a constant amount of time. We're adding 1 to the size variable, which is also a constant time operation. So these 2 things basically boil down to constant time operations. So I'm going to kind of bundle those together and say that basically we would think of those as taking a constant amount of time. It's not dependent on our problem size n. It's just 1 unit of whatever our units are. So again, for our minimum amount of time, that's kind of the path we take. So for our omega, we could kind of think of it as being an omega of 1. But we also have to figure out our worst case scenario. And our worst case scenario would do that if statement, and we're dependent on whatever is going on in that if statement. So let's go ahead and take a look at the if statement and figure out what's going on there. So in the if statement, it will call this other method called grow. So we need to figure out what's going on in grow to figure out what our add is going to do. So we'll search for grow and we'll find the place where it's defined. So, so it's going to create a new array and return it, it looks like. And we give it some sort of a minimum capacity. So the minimum capacity is the desired minimum capacity, and it may throw an exception if the computer runs out of memory. So we can look through the details here, and we can see that there's an if statement. Everything being checked in the if statement is just a simple comparison. All of those we can argue are constant time operations. Then it calls another method, ArraySupport.newLength. And it passes in a couple of different variables, the old capacity, a difference, the amount that it may need to grow. And here it's doing old capacity, and it's doing this thing called the right shift operation. Basically, this is just a trick to do a multiplication by 2. At the end of the day, the array list is using the strategy that we saw in Studio, where it will double the size of the array when it runs out of space. To confirm that, we would probably need to look at the details of this new length method. And those are available to us. It's doing a maximum of some values. It's doing a little bit of math here. It's not doing anything really dependent on the size of the array. It then calls another function, another method, that is also just doing a simple couple of if statements. At the end of the day, this is really just trying to decide how to increase the size of the array. And I'm going to gloss over all the details and mechanics of how it does it. For our purposes, we can just think of it as doubling the size of the array. So when we add something, it may choose to call this method to grow our array. The method will try and decide on the capacity that we need, and it will take one of two paths. It'll either do this if statement or the else clause. I'm only going to focus on this part. We could do some analysis and demonstrate that for our example, this is really the part that's of interest. I'll leave that to you. The part that's really critical here is it calls arrays.copyOf. Just like before, we've got this abstraction. We'd have to dig into the details and figure out what's going on here. But again, I'm going to kind of simplify this, and I'm going to say that basically this is creating our new array with twice the capacity, and it's copying everything over to it. I'm going to say that at the end of the day, we can think of this as being 2n operations, but we're going to drop all of those coefficients and just focus on n. So to summarize, I'm going to say that this growing process in our example program is an O of n operation. And it's always an O of n. It's never any better than that for our particular example. Okay, so with that, let's let's go ahead and go back and think about our overall add. So our add calls this other add, and sometimes this other add does no work whatsoever. It skips past the if statement, it just adds the item, and it's constant time. Every once in a while, we're out of space, and it calls the grow method, which is order n. Okay, at the end of the day, we can now kind of estimate what our add is. We know the best case and the worst case scenario. Okay, so best case, constant time. Worst case, n units of time, where n represents the number of elements in our array. Okay, so let's take a quick look at get. Okay, so here's our public get method. So it calls objects.checkIndex. So we do need to look at this and look at all the details, but I've already done this, and this is just a constant time operation that confirms that the index is valid for the size of the array. And then it returns element subdata. So notice that this is a function, so let's go ahead and search for that. So the function, all it really does is it looks something up in the array and returns its value. So again, arrays have the random access property, and retrieving an item from any particular index is considered constant time. Okay, so that just leaves us with remove. So let's go ahead and search for remove. And here is the remove that removes at a particular index. This is the one that's used in our sort. Again, it verifies that the index is valid, and that's a constant time operation. It creates a variable that refers to the array, and then it does something called a fast remove. So let's go ahead and take a look at what fast remove does. So fast remove does adds 1 to something, so that's a constant time operation. It does an if statement, and then depending on the outcome of that if statement, we'll call system.arrayCopy, and then it does an assignment to an array. It assigns null to a particular position in the array. So most of this is constant time operations, assigning something to an array and adding 1. But of course, the system.arrayCopy is going to take some time. Basically, what it's going to do is it's going to move all of the elements in the array over by 1 to fill in for the item that's being removed. So if the item being removed is at the beginning of the array, it's going to shuffle everything else in the array over by 1 to compensate. So if we've got n elements in our array, essentially this is going to do n operations to move all of the n-1 elements over and to add a null to replace the item that was removed. Okay, at the end of the day, we can argue that this is a order n operation. Okay, so just to summarize, we've identified that our size operation is basically a constant time operation, and add really depends on whether we have to increase the size of our array or not. A lot of the time, it's a constant time operation, but occasionally we have to double the size of our array. The get operation is essentially always a constant time operation, and the remove operation, if we're removing the very last item, will be a constant time operation. Otherwise, an if statement will execute something that shuffles over all of the items after the item were removed and kind of moves them in place of the item that was been removed. So in the worst case, we remove the first thing and we have to move over all of the remaining items, so it'd be a order n operation. Okay, let's go through the same basic process with parts of the linked list. So here's the source code for Java util linked list. So again, I'm going to search for some of the basic operations we're using. Before I do that, I'm going to take a quick look at the linked list to get some sense of how it's implemented. So just like the array list, it has an integer that represents the size, so it's going to keep track of its size at any given time. In this case, it has a node that points to the first item in the list, a head node, and a node that points to the last item in the list. So this is very comparable to what we've seen in studio activities. So let's go ahead and take a look at the size method, and we'll see a very familiar pattern. It just returns the contents of the size instance variable. Let's go ahead and look at the add method that we're using. So the add method calls another method called LinkLast and returns true. So the total amount of effort is all taking place in LinkLast. Return true is a constant time operation. So let's go ahead and take a quick look at LinkLast. So LinkLast creates a new node, which we'll consider to be a constant time operation. And then it assigns a variable to the new node. It assigns last, the tail pointer, to the new node. And then it possibly updates first or updates a next variable and adds 1 to size and adds 1 to mod count. Again, we could kind of think of these as all being constant time operations, so we'll decide that LinkLast will claim that it is constant time and that consequently adding, appending to the end of the list, is also constant time. So let's take a very quick look at get, and here's the first method that we'll see that's a little bit of a departure from what we've seen so far. So it calls a method to check the element index. So we've already seen things similar to this in the array list. And then here's where something more interesting goes on. It calls a method called node with the index. So again, to understand the time complexity, we need to delve into the details of both of these. I'll claim that the check element index is constant time. Let's look at what node is doing. So it's given an index to search for. So we'll find where it's declared. There it is. So it's got an if statement, and the if statement is actually just checking the index to see if it's before the midpoint of the list or after the midpoint of the list. And it'll either do this branch of code or this branch of code. In either case, there's a for loop that it's doing. This for loop is counting upward from 0 to the index. This for loop is starting at size -1, the end of the list, and counting backwards as long as we're greater than the index. So the people who devised this came up with kind of a clever way of trying to cut our work down. If we know that the index is less than halfway through the list, we'll start at the list and move towards it. If it's more than halfway through the list, we'll start at the back and move towards it. So we'll never have to traverse more than half of our list. Okay, so, but in the worst case, the element we want is at approximately the center of the list, and we'll have to traverse over half of our items, our n over 2. Again, we'll drop constant factors, and I'm going to claim that this entire process is order n in the worst case. Okay, so let's also take a look at our remove, and so we're interested in a remove by index. There it is. So the remove by index, again, uses that node function to find the particular node to remove, and then it calls another method called unlink. So I'm going to claim that unlink is relatively simple and straightforward, and that all the work is taking place in that node method that we just looked at that may have to traverse through half the list. Okay, so to summarize our linked list operations, the size is always constant time. It's just returning that size member variable. The add is always appending to the end of the list, which we have direct access to through the tail variable, so it's also constant time. Get really depends on where the item we want to get is. If it's the very beginning of the list or the end of the list, we can consider it essentially constant time. But the typical case is that the item is somewhere in the middle. And if it's in the very middle, we're going to have to go through half of our list, so n over 2 items, so we'll consider the worst case to be approximately n operations. And remove, we can go through the exact same argument because remember it still uses the exact same method to access the item that gets removed. Okay, so let's do a quick comparison of our two different lists types. We've got the array list and the linked list. And we see that in many ways they're very comparable. Size is constant time for both. The linked list has a slight advantage when we're adding things to the end. So the append operation tends to be better for the linked list, although if we're appending many things, on average, the time to append to an array list isn't bad. Remember, this is only the worst case, and it happens somewhat infrequently. We can see that there's a big difference in the get operation's worst case. So in the linked list, get really depends on where the item is in the list, and oftentimes it's order n. Remove by index, exact same argument as get. Typically the linked list is worse. So the get is one of the things that arrays are really, really good at. Remember, arrays have that random access property, which allows us to access an item in a particular in constant time. Okay, so let's take what we've learned and come back and analyze our selection sort with both the array list and the linked list. So first I'm going to kind of scan through this and look for things that are particularly noteworthy. So remember there's this outer while loop that goes until the input list is size 0. And I'm going to use the size of the input list as our n, as our problem size. So everything that's done in this loop basically gets multiplied by n. So I'm first going to kind of make a note of that all of this stuff is going to be multiplied n times or done n times. So I'm going to kind of group it all together here, and I'll put a little indicator that this is all being done n times. So all that's done n times. And again, that's kind of an upper bound. In this case, we're moving one item at a time, so it truly is being done n times. I've also got this inner for loop that starts at 0 and counts up to the size of the input. And the input's going to get smaller and smaller because we're removing things from it. But the first time through, this will go through all n items, and then the second time it'll be n minus 1, then n minus 2. And we know from our previous studies that this is approximately n squared. I'm just going to assume that it's always doing this worst case. Again, I'm kind of overestimating this. So in terms of the ideas here, I'm kind of computing the big O as a worst case scenario. So I'm going to assume that everything inside this inner loop is also bundled together and is being done n times. Okay, and with that, let's break it down and look at our individual operations. So we know that with the array list, the min and the max of getting the size is basically 1. We'd consider assigning a value to a variable to be a constant time operation. we'd consider setting I equal to 0 to be a constant time operation that occurs before the loop executes. I'm going to kind of assume that that's already accounted for here. Every time the loop executes, we'll be checking our size. It's really important to think carefully about the method calls that are happening in loops. But again, we've already identified that this is a constant time operation, and every time through the loop, it's going to be adding 1. 2 constant time operations, I'm going to use a 1 to indicate that all lumped together, that's a constant time thing. Then inside the loop, there's this if statement, and it will be doing a get and another get. So both of these are from the input list. And we know with our array list, it's using that random access property of arrays, and it can access items in constant time. So we'll consider that constant time. We'll also consider the assignment to a variable, a constant time operation. Okay, so let's look at the things that happen after that loop is done. So there's this line here that actually has 2 things going on. It gets something from one list and adds it to another. So the get operation would be constant time for the array. Again, random access property. The add operation, if we're lucky, it's pretty fast, and we're just adding something to an available space. But if we're not lucky, we have to increase the size of our array, and it's an order n operation. Again, we simplify these. So we'd consider one of them to be order n, and the other one just 1, constant time. And then there's a remove on a list, and we know that the remove, if we're lucky, it takes constant time if we're just removing the last item in the list. And if we're not lucky, we have to shuffle nearly everything in the list over, and it takes n units of time. Okay, so with that, we can actually kind of compute a total here, basically just by adding everything together and multiplying through. So first I'm going to write this out as kind of a full equation, then we'll just kind of simplify it down to the meaningful part. So I'll do the min time, and then I'll do the max time. And then I'll simplify both. So first I'm focusing on the array list. Okay, so it's a constant time operation plus, oh, this thing's inside of 2 loops, so it's being multiplied by n by n. And that's happening for this and this and this. So we could think of that as 4n squared. And again, we'll eventually drop all the constants here. Then this and this are also just being multiplied by one of the 2 n's. So plus another n plus another n. So at the end of the day, it looks like this is n squared, right? And notice that I'm using the little caret symbol to indicate squared here since I'm typing in text. We could go through the same process for the maximum stuff. And we'll notice that basically it's the same for everything up through this inner loop. But then when we're outside the loop, this is not n times 1, but it's n times n, plus an n times an n. And if we kind of simplify all that down, we basically end up with 6n squared. But again, we can kind of think of that as just being an n squared thing. Okay, so it looks like in the best case, we have to do approximately n squared operations, and in the worst case, we have to do approximately n squared operations. So let's go through that with the linked list as well. So just like before, the size is a constant time operation. It keeps track of that in a variable that just gets returned to us. The assignment of the variable hasn't changed from the 2 versions. The basic mechanics of the loop don't change between the 2 versions. But the get is where things change. So again, this is doing 2 different gets. And if you remember with the linked list, it has to start at one end of the list or the other and go until it finds the item. So in the minimum amount of time, it'd be nearly constant time. But for the most part, we have to kind of assume that it could have to go through half of the list and be on the order of n. And then again, we've got an assignment of a variable that hasn't changed between the 2 versions, so that stays the same. Okay, so with the list, adding on to the end is constant time pretty much all the time. We don't have to worry about occasionally having to double the size of the array. And the removal of something using an index has to traverse through the array in the exact same way that the get does. So if we're lucky, it's either at the very beginning or the very end. If we're unlucky, we have to go halfway through the array. Okay, so just like before, I can kind of compute totals here. I'm going to cut to the chase here. We've got an n times an n times an n. So that will be our true worst case. Now in our best case, our absolute minimum time will be back to n squared. But our worst case, which we are seeing, is n cubed. So if you remember, the performance between these two was vastly different, and it's because one of them is an n squared algorithm in the worst case, and the other one's an n cubed. Okay, and it turns out that when we're repeatedly going through a lot of data, we're just never going to see this. We won't see this minimum very often. I mean, it'll happen when we're accessing the very first to the last item, and but we'll have to go through all of our data, and this will typically perform with this n cubed sort of performance. Okay, the other key takeaway here is I've identified one of the main reasons why the linked list is performing poorly. So it's because I'm doing a get operation, and the linked list just isn't very good at the get operation, or at least not in comparison to the array list. It turns out we could actually just restructure this loop and avoid this problem. Okay, so here's another variation of our selection sort, and we'll use what we just learned about the deficiencies of the get for the linked list, and this has been rewritten to avoid the use of the get. It's only got a few minor changes. It still uses a while loop and it goes through until we've removed everything from our input. It still is going to keep track of the index or the location of the minimum item in our input collection. But we've added a new variable to keep track of where we're currently at, what the index we'd currently be at is, and we've added a variable that represents the minimum value we've found so far, and we'll initialize it to the maximum possible integer value. So anything we find will be less than or equal to this. Okay, and here's the real important change. We've changed the for each style loop instead of an index-based loop. Linked lists aren't particularly good with indices. The for each style loop is it uses a data type and a variable of that type and a colon and the name of the collection it's going to be iterating through. And the people who designed the array list and the linked list, they included support for something called an iterator. And an iterator is an object that is efficient at iterating through the list. The for loop is automatically translated and adjusted to use this underlying iterator stuff. The good news is, from a programmer's point of view, you just focus on the concepts. I've got a list of integers. I want to iterate through each integer and store each one in a variable so I can work with it. And then the underlying details about doing that efficiently are handled for us. Okay, then inside the loop, it's essentially doing the same types of things it did before. It's comparing the item it's currently on to the best it's found so far. If the item it's currently on is better, it will save it away as its best, and it'll also keep track of that location. And as it moves through, it's keeping track of the current index. So the current index variable is kind of replacing our loop variable in our previous version that was counting, our I that was counting one at a time. At the end, it still does exactly what it did before. Okay, so the for each style loop with the linked list overcomes the deficiencies of using get. It turns out that the for each style loop can iterate through the linked list quite efficiently. Okay, so let's repeat the test case that we had earlier where we've got linked lists for our lists, and we're adding the 3,000 random values, but this time we'll use our better selection sort that doesn't use index-based gets. We'll go ahead and run it with the linked list. Done, done, done. So it's really fast. And we can now change it back to the array list, and we'll find out that we have very comparable performance. Done, done, done. So by avoiding the operations that the linked list is poor at, we've got the two different implementations having roughly the same performance.